Well, good evening. I'm Dave, KE4EA, and we're continuing on in our extra class series. Tonight we're on Chapter 6, and we're going to be doing Chapter 6 in two parts. So this is Chapter 6, Part 1. If we have any YouTube students that have found their way to our channel and you're not on our mailing list, please contact myself or Gary so that you can get all of the announcements for the upcoming meetings. So I just wanted to say that if you're not getting our weekly emails, then you're not on our list. So we'll go from there. All right, so tonight is about radio circuits and systems. We've been talking about individual components and the way that the components act. And tonight we're going to start putting these components together into subsystems that form the basis of ham radio. The amplifiers and signal processing will be the first two sections for tonight, and then next week we're going to do 6.3 through 6.5. This chapter, interestingly, is I think just about the largest one in the book, so there's a lot of information that winds up on the pool questions. So be sure to pay attention to the blue text as we get there. Most of the questions, pool questions, are fact-based questions, so tied to theory. There's a couple of calculations tonight, but they're extremely easy, so nothing to be afraid of. In fact, I won't even be showing them on the calculator cam, but a couple of things for you to do there. So we're going to be doing this tonight, and then next week we're going to start out with software-defined radios. So that's going to be an interesting session, since that's really taken the radio market by storm. So amplifiers, lots and lots of amplifiers are used in ham radio. Here's just a few of them. We've got RF amplifiers, intermediate frequency amplifiers, audio. Got high power and low power. Here's a KPA 1500. It's Elecraft's 1500 watt amplifier. And here's a 741 operational amplifier. So there's a couple of pictures there. So amplifiers have a characteristic known as gain, which is the ratio of output to input voltage. In other words, are we making something louder? If yes, how much? Amplifiers can have differing input and output impedances, and that's how they're used in circuits sometimes. They can use all kinds of components, transistors, tubes, ICs, all part of the family. I like what Kastler says about amplifiers. They make things louder. So that's a pretty big, pretty all-inclusive statement there. Just wanted to do a little bit of review here because it'll come into play when we talk about some of the amplifier circuits. So this is pretty basic, but we're going to have a 10-volt battery across two resistors in series. So, and we're referencing to ground. So between this point and this point, it's right across the battery, 10 volts. And because these resistors are of equal value, there's going to be 5 volts from this point to ground. Be a voltage divider that just divides by 2. So that's pretty basic, but we're going to see several different, we're going to see voltage dividers applied in several different contexts this evening. And another one that might be a little bit less obvious, what if we take the same 10 volts but make it AC now, alternating current at 1 kilohertz? Well, we're still going to get 10 volts AC across the top, but I've changed something here and added a capacitor, a 10 microfarad capacitor. And if you work out the capacitive reactance at 1 kilohertz, it works out to about 6 ohms. So what we have AC-wise is almost the entire signal developed across this resistor, 9.99 volts, and the rest of it is bypassed to ground. And this is going to come in handy in some of our amplifier discussion coming up. Now, Kastler had a point that I found it to be extremely helpful. That's considering amplifiers as 3-terminal devices. And we'll see how this is applied. So a 3-terminal device is, we've got one terminal that's common between input and output. So the input is across terminals 1 and 3, output across 2 and 3. All right. So how do we apply that? Well, we're going to plunk a transistor into that circle. So in this case, we've got what's called the common emitter case, and you'll see that that's in blue. We're going to need to identify what a common emitter configuration is for our pool questions. So we've got the input across the base and emitter, and we've got the output across the collector and emitter. You can see why it's called a common emitter. And then we're going to rotate this 90 degrees. So now the base is the common element between the input and the output. You can kind of see how that works. This is called the common base configuration, the input between the emitter and base, output between the collector and the base. And you can probably figure out what's coming next. This is the common collector configuration, where the output is on between the emitter and the collector. This is also called a emitter follower circuit. And you can kind of tell why, because the emitter is the output. This is used primarily for impedance matching purposes. The same thing applies to field effect transistors in tubes. With a field effect transistor, we've got the gate, drain, and source. So we can have a common gate, common drain, common source configuration. Some of you have probably heard of grounded grid amplifiers, power amplifiers in amateur radio. So that also, all of these technologies can be viewed in the three-terminal device context. So some people might be saying, well, why do we need all of these different configurations? Well, there's different performance characteristics, there's different gain. Some are just used for buffer amps, and some are used for impedance matching. So these are just tools in the designer's toolbox. Spent a little time on the common emitter circuit, and as I said in the email that I sent out, our license manual goes into just painful detail about how everything flows through all of the resistors and capacitors and what happens when. I'm going to be simplifying that rather dramatically. If you're into that sort of thing, the book is excellent, but it'll take you a while to get through it all. Most of you, I think, are more interested in just getting your license and don't want to get into that level of detail. This could easily be a semester college class, so we're going to simplify it, really focusing on what we need for the pool questions. So the input is to the base of the transistor. Output is from the collector. Here's the collector. And this is the common emitter configuration. You'll see this configuration the most often in schematic diagrams and circuits, and it provides the highest gain. Now here's our voltage divider back again. You notice it's in blue. The purpose of R1 and R2 is voltage divider bias. Well, let's see if we can figure out what that means. Well, here's the positive supply, and here's ground. It says R1 and R2 provide voltage divider bias. You may recall that for this kind of a transistor to operate, the base has to be more positive than the emitter by about 0.6 of a volt. So these resistors set that point where the transistor is going to operate. That's called the bias point. The purpose of R3, now this is kind of interesting because as the transistor conducts, there's going to be a current flow from the power supply through ground going through the transistor. So a transistor doesn't like to get overheated. The hotter a transistor gets, the harder it will conduct. The more it conducts, the more current can pass through it, and eventually you'll get to a stage called thermal runaway where the transistor can burn up. So what happens as the current increases through the transistor, the voltage across this resistor, R3, just via Ohm's law, as the current increases across the resistor, what happens is the voltage will rise across the resistor. Okay, that will increase, it'll bump up the emitter relative to the base, which will serve to turn off the transistor or slow it down or cut it back a little bit, protecting it. So in this particular case, it's called self-bias. So this adjusts the operating point of the transistor according to how hard it's conducting. Two things you need to make note of there. Now the DC bias and gain concept Let's assume that the transistor is in full saturation. That's this point here. It's conducting just as hard as it possibly can. At the other extreme, it's at cutoff, where it's not conducting at all because of the voltages that are present. So what we want to do for the most common amplifier configuration is pick a point that will put turn the transistor on about halfway. So I put some arbitrary voltages in here. So we can see the transistor is conducting, so we got 4 volts and 4.6. Be a voltage drop across the base emitter junction, which is an indication that it's probably working. So it's right in the middle. So if we vary the voltage into the transistor, or if we move it up or down, that will cause it to conduct to a greater or lesser extent. So maybe a 1/10 of a volt change here might wind up in a full 1 volt change on its output. We'll diagram that in more detail. But we start out turning the transistor on about halfway. This would be for a Class A amplifier, which we're going to talk a lot more about coming up. So we've removed the AC signals here, and we're just looking at it from a DC point of view. So let's assume that we have a gain of 100. In other words, we're going to amplify the input by 100 times. So if the base moved up by a 100th of a volt, the voltage at the collector may change by about 1 volt. Well, that's a ratio of 1 to 100. So that illustrates what's going on here from a DC point of view. Now this is the same diagram, the same DC bias that we saw, but now we're going to add the AC component. So input is here, output is over here, and this capacitor is what would be called a coupling capacitor. It'll pass AC into the transistor, but none of the DC, the bias for the transistor, will be injured in any way by what's hooked up to it, because this capacitor will block any voltages on the input just past the AC. Similar for the output. So again, we're going to put an AC signal in here that's varying plus or minus 0.01 volts. So we saw in the previous slide we were at 6, so our AC voltage would be that plus or minus a 100th of a volt. And that'll swing the output by about 1 volt, and gain of 100. So here we've got a picture of the input signal, and here we've got a picture of the output signal. So it makes things bigger, as we said. Another interesting fact about this type of amplifier is this is an inverting amplifier. So as the signal goes positive on the input, it's going to swing negative on the output. This is the characteristic of the common emitter. Okay, and here we're showing how those voltages are swinging on the input and the output. And as I mentioned, the capacitors look like open circuits to DC. They provide DC isolation to the stages before and after. Now the high value caps will look like a short circuit to AC. In the diagram that I showed you, the very first slide, we saw that this capacitor here was practically a short circuit to AC, and all of the output signal was developed across this resistor here for maximum output to the next stage. If this capacitor wasn't here, that might be half the signal. So that's an important capacitor to have. So that's the common emitter circuit. And I'm going to give you a shortcut so that you can recognize it instantly. You can go ahead and figure out the flows. We see that the input is on the base to ground, here to here, and the output is between the emitter and the collector, making this the common emitter configuration. So you can figure it out that way, or I'll give you some shortcuts to make it even easier. Now, common base, what we've done is we've rotated the transistor just 90 degrees. This is its configuration. Input on the emitter, output on the collector, emitter, collector. It has a low impedance input and a high impedance output, so this is commonly used for an impedance converter. And in this case, the input and output phase is the same. As this rises, the output rises. There aren't any pool questions related to this. I just wanted to go through each of the three configurations to compare them. Common collector, now this one we'll see a little bit more frequently, also called an emitter follower. So you need to associate common collector to emitter follower, and you can see that the signal is coming out of the emitter. The input and output signals are in phase. The only configuration where they're inverting is in the common emitter version, the first one that we talked about. Output coupling capacitor is over here. Again, it keeps any DC components that we're feeding from affecting this circuit. Often used as a buffer, something in between two stages. For example, an oscillator circuit can be very sensitive to anything affecting it, shifting its frequency, and so a buffer is commonly used to make that not an issue. Now, how do we identify the common emitter configuration? This is the shortcut that I promised you. When you see the configuration here, and this is just the way they're drawing it in the book, so I'm giving you a shortcut or a cheat or a memory aid, whatever you want to call it. When you see this configuration with these capacitors coming out, these are basically one right above the other, sort of in a parallel configuration, not connected in parallel, but you can see that they're diagrammed that way. That will instantly tell you that you're dealing with a common emitter, and there is one pool question that will ask you to make that identification. Now, in comparison to tubes, or vacuum tubes in comparison, we've got the plate corresponding to the collector, and you may notice that we went through that whole section pretty quick. That's several pages in the book, so you can get a lot deeper than that, but I'm giving you what you need to get a basic understanding and point you directly to the pool questions that are related, so you're welcome. So anyway, in a tube, we've got the plate that corresponds to the collector, we've got the grid, corresponds to the base, the cathode corresponds to the emitter, so we've got configurations that can be used there. So the common cathode amplifier, just like the common emitter amplifier, high impedance and power gain, or in the case of the transistor, voltage gain. And the grounded grid amplifier. Now, the reason that this one is probably in the pool is because it's a real common configuration in tube-type amplifiers. It has low input impedance, and most transceivers have an output impedance in the neighborhood of 50 ohms. That would be considered low impedance. So you'd want a high-power amplifier to follow your transceiver that would have a fairly low input impedance. This would be the amplifier. Matches well to 50 ohms. So grounded grid amplifier, low input impedance. And you can think, just remember that that's typically how you'd want to use it. Output of your transceiver, your transmitter, into a bigger amplifier. And right on to some questions. We'll see if any of this stuck now. In figure E7-1, what is the purpose of R1 and R2? R1 and R2.
Bravo.
Bravo, voltage divider bias, and thank you for giving us the 3 seconds. In this figure, what is the purpose of R3?
Delta.
Delta, self-bias, keep the transistor from burning up. Well, some of it is sticking. This is wonderful. What type of amplifier circuit is shown in this figure?
Charlie. Charlie.
Charlie, yep. And you can either do that by figuring out the signal flows, or just remember my shortcut trick of these two capacitors appearing that way. What is a characteristic of an emitter follower or common collector amplifier?
Delta.
Delta. Okay, input and output signals are in phase. The only one that is out of phase or inverting is the common emitter. What is a characteristic of a grounded grid amplifier?
Charlie.
Charlie, low input impedance. This is really complicated when we look at it in the book, but it's not so complicated when we boil it down. So I'm glad you're all following. All right, and that moves us on to a fascinating area called operational amplifiers. This is really fun stuff. That operational amplifiers can do tons and tons of things. I've listed some of them here. I'd like to call this the Swiss Army knife of amplifiers. It can serve as an AC amplifier, a DC amplifier. It can be set up to operate as a filter or a comparator. We're going to be, all of these things are going to be important as we move forward. It can be used for impedance matching. It can be set up to be used as an oscillator. So there's a Wikipedia article here that's got all kinds of additional information. So this is the lowly 741 operational amplifier. These are available for less than $1 a piece. You can get a whole bag of them for a couple of bucks. And they're kind of fun to play with. When you see what some of the options are, if some of you are into playing with the electronics, this type of a project board or perf board, you can plug the part in, you can put resistors around it and capacitors, power it, and then hook up test equipment and see what it's doing. So this is a real wonderful learning tool if you care to go further. So why are they called operational amplifiers, you might be wondering? Well, back when they were first came into being, or first invented, I guess you could say, they had a characteristic where they could be configured so that the input to output relationship could have been squares or square roots. In other words, you put in a certain amount of voltage and the square root of that voltage would appear on the output, or logarithms, multiplied, all kinds of that. So these mathematical operations is where the operational amplifier term came. Of course, this is all analog functions, but that was its genesis. So we talked about all of these things. Yes. Okay, now we're going to get into some more details. Now here's some scary sounding words. Okay, an operational amplifier is a high gain, direct coupled differential amplifier with very high input and very low output impedance. Well, let's unpack that a little bit and see what in the world they're talking about. That way the answer to the pool question in blue here will make a little bit more sense. By high gain, operational amplifiers can have up to 1 million times output to input. Very high gain. Now, direct coupled means that a DC voltage at the input will have something to do with the DC voltage at the output. Remember, in our common emitter amplifier, we had coupling capacitors going into it and coming out of it. In this case, the signals are direct coupled internally. So this is the non-inverting input, so if we move the voltage on the non-inverting input up 1/10 of a volt, the output would go down by 1/10 of a volt if the gain was 1 or unity. So it's direct coupled. That means what happens on the input DC-wise is going to show up on the output DC-wise. The level will be according to the gain of the circuit. Okay, so high gain, direct coupled, differential amplifier. Okay, what does that mean? Well, we've got these two inputs called the inverting and the non-inverting input. So the amplification that occurs is the difference between those inputs. So that's what they mean by differential amplifier. Very high input, that's this side, and very low output impedance. So now hopefully these words make a little bit more sense. So the op-amp will amplify DC as well as AC. We talked about the inverting and non-inverting inputs. And we talked about the fact that it amplifies the difference between the two inputs, kind of breaking this statement down a little bit. we've got something else here called R sub F. That's called a feedback resistor. Notice that that's connected between the output and the input, the non-inverting input, or the inverting input, excuse me. And we're going to see coming up that the gain of this device is simply the ratio of these two resistors. So here's some amazing things. We're going to talk about ideal op amps, the ideal op amp, and then what we have in real life. Now, an ideal op amp has infinite input impedance. Pretty handy, wouldn't load down a circuit. In the real world, the answer is very high input impedance. Zero output impedance, ideally. It's going to have very low output impedance. So these are the within the context of the way the pool lists them. Infinite voltage gain can be as high as 120 dB. We're going to talk about open loop and closed loop, but just the important thing here is that these devices can have extremely high gain. Gain does not vary with frequency. In fact, in the real world, gain decreases with frequency. Ideally, zero output when the input is zero. In other words, the inverting and non-inverting inputs are the same exact value. Should make the output go to zero. In truth, there's usually some amount of output with zero input. So here's some things to grab onto. Op amps are primarily a low frequency device. You don't normally see them used at RF. They're good up to maybe 10, 15, maybe even 100 kilohertz, which is low frequency. So you'll see them very often in audio applications. So here's the basic circuit. We've already seen that. I'm concentrating here now on these two resistors, the feedback resistor and the input resistor. So gain and frequency response are determined by the feedback components. In this case, we just have resistors, so we wouldn't think that there would be any frequency response or frequency modification taking place here, because there aren't any reactive components, inductors or capacitors. So the voltage gain is determined by these values. In this case, the circuit is using the inverting input, so the result will be negative. So if this goes up by 1/10 of a volt, this will go down by some amount of voltage, depending upon the gain of the circuit and determined by the ratio of these two resistors. If that sounds scary, it isn't. I'll show you why. And here we've got a case, it's the only pool question like this, a capacitor across the feedback resistor will make the frequency response of the circuit a low-pass filter. Now these can be configured for low pass, high pass, all kinds of crazy things. There's whole books that have been written about things you can do with op amps. One was called the Op Amp Cookbook, I believe. The ARRL, or not the license manual, but the handbook, the ARRL handbook, has got a fairly decent sized section of all the different things you can do with op amps. But this one you'll need to recognize. Capacitor across the feedback resistor will make it act like a low pass filter. Now we've got a closed loop. A closed loop configuration is when this feedback resistor is in place. Now here's a gain calculation. In the pool questions, there's I think 3 or 4 of these. They're extremely simple. So let's look at this one. In this case, the feedback resistor is 68K, 68,000 ohms. R1, the input resistor, is 1,800 ohms. And the gain is just 1 divided by the other. So 68K, okay, R1 is 1.8K. So you just divide 68K by 1.8, 68 divided by 1.8, you wind up with 38 rounded. So the gain of this circuit is 38. So in our case, for the exam, for the pool questions, in every single case, it's the bigger resistor divided by the smaller. So you don't have to figure out, well, which one is R1, which one is RF, how do I apply this formula? It's always the bigger resistor divided by the smaller. It just works out that way. So another shortcut for you. And you may notice that this formula is not on our extra class reference sheet. That's because it's so easy, you really don't need it. All right, now we're going to do as another output voltage calculation. All right, and you can see right off the bat that 10,000 to 1,000 is going to be a gain of 10, right? 10K divided by 1K equals 10. So let's use an input voltage of 0.23 volts DC. Now this is probably the most complicated example we're going to talk about tonight. And it's really not that complicated if you just kind of think through it. So track with me here. Use an input voltage of 0.23 volts DC. So you might just pause for a minute and say, I wonder what that means. If we're going to have a gain of 10, it means the output's probably going to be 10 times that value, right? All right, and because we're putting in 0.23 volts on the inverting input, what do you think we'd have on the output? Well, it's going to be a negative. So let's see how that works out. So 0.23 volts times 10, the gain, equals 2.3 volts. But we're on the inverting input, so the output will be negative, or 2.3 volts DC. And hopefully you followed along with that. We've got the input voltage times the gain to give us the 2.3, and because we're on the inverting input, it's going to go in the opposite direction of what we're putting in. So we're putting in positive 0.23, we're going to be driving the output negative by 2.3 volts. Now, I promise this is the most complicated thing we need to worry about here, but if you take it step by step, it's easy to work through. I added this note here. The only reason I did is because we had a student in the past ask about this. There's a reference in our extra class license manual that talks about a virtual ground. And we're not going to get into that at all because it's way beyond what we need to dive into. But there is an article here if you care to follow that up. So I gave you a link. All right, now let's consider the open loop. Now, first thing we'll notice is that there is no feedback resistor between the output and the input. Okay, that's the open loop configuration. A closed loop configuration will have that feedback resistor. Now, the key thing to know about a comparator is that when the input voltage crosses the threshold voltage, the comparator changes its output state. All right, well, let's dig into this a little bit. So we're setting a reference on the non-inverting input here. We've got a resistor R1, R2. So we've got 12 volts. And these are equal value resistors. We'd have a 6 volt reference point that appears on pin 2. Okay, we'll hold on to that for a second. 6 volts is our reference. When input voltage crosses the threshold voltage, which is 6 volts, the comparator changes its output state. So we're going to say that until that happens, we're at 0 volts, or we're going to be low. When we exceed that 6 volts, it's going to switch. I actually said that backwards. Let me get my reference notes here. See, we're at 6 volts here, and when we exceed that value here, it'll drive the output low. Now, hysteresis, I liked Kastler's definition. Another concept for us here. Hysteresis is time lag in response to some action provided by R3. So what happens when this comparator switches, we were at 6 volts here, but what's going to happen when the output goes low, that reference is going to get even lower. So it might drop to 6.8 volts. So where we're at 6, we're going to put an additional resistor, it'd be like in parallel with R2, and that'll change the reference voltage to something like 5.8, just in my example. Well, what that means is there's now a bigger difference that has to occur before this switches again. So before, if this was at 6.1, now it doesn't need to be that much. So this is the resistor that tends to pull that output low, and it changes the relationship between these two. So why would we want that? Well, hysteresis prevents noise from causing unstable output signals. So if these two inputs are very, very close together, just a very slight difference between them, or something like key bounce on a switch that Gary talked about, I think last week, that would be driving this thing crazy. So that's why you want you need a greater input to make that change. And the example that I like to use is a thermostat. It kind of brought it home to me. So if you've got a thermostat set to 70 degrees in your house, if it was 75 degrees in your house, the air conditioner would come on and work until the room temperature got down to 70 degrees. Okay, well, that makes sense. But you don't want it to come back on when it gets to 70.01 degrees, okay? You want to wait a while. Maybe you want the thermostat to get up to 72 or 73 before it kicks in again and brings your house back down to 70. That's the concept of hysteresis. And by the way, some electronic thermostats, that's a setting that you can actually change to change those values. So that's the concept. So the things that we need to know for the pool: when we cross the threshold voltage, the comparator changes its output state. And hysteresis prevents noise, like in the air conditioner example, the thing switching on and off rapidly, or more rapidly than you'd like, would be equivalent to the noise. Hysteresis prevents noise from causing unstable output signals, or rapidly fluctuating output signals. So a little bit more on open loop, so that we had no feedback resistor. And then the concept of input offset voltage. We saw in the case of the ideal op amp, if the inputs were identical, the output should be 0. Well, that's not usually the case. The input offset voltage is defined as the differential input voltage needed to bring the open loop output voltage to 0. There'll be a slight adjustment here in order to achieve that state. Now that's a definition. How much do we need to pad it, if you want to call it that, in order to get it to 0? That's the input offset voltage, and these would all be in the spec sheets of the parts that might be interested in using. And also we saw with the ideal op amp that the gain did not vary with frequency. In the real world, the gain does vary with frequency. The higher in frequency that you go on the input, the lower the output's going to be. And at some point in time, and you get to a certain frequency, let's say it's 100 kilohertz, at the output, you're feeding at 100 kilohertz at 1/10 of a volt. At some point in time, the gain is going to be reduced until you get that 1/10 of a volt on the output. So the frequency at which open loop gain equals 1 is defined as the gain bandwidth. So we slowly turn up the frequency, increase the frequency, the output is going to get smaller and smaller until the input and output are the same. That's defined as an open loop gain of 1. The input and output are the same. So these are the words as they'll appear in the pool. Speaking of which, what is the typical output impedance of an op amp? There's kind of a trap in this question, but we'll see if we can avoid it.
Alpha.
It is alpha, very low. Some people will look at that and say, well, 100 ohms, that's pretty low compared to this, but very low is the answer that we want. What is the typical input impedance of an op amp?
Delta.
Delta, very high. Yep, very high. What is the frequency response of this circuit if a capacitor is added across the feedback resistor?
Bravo.
It is Bravo. It's a low-pass filter. It's just one of those things you need to memorize, I guess. What is meant by the term op-amp input offset voltage?
Charlie.
It is Charlie. The differential input voltage needed to bring the open loop output voltage to 0. And what is the gain bandwidth of an operational amplifier?
Bravo.
It is Bravo, the frequency at which the open loop gain of the amplifier equals 1. We're doing really, really well. Now here's some calculations. I wasn't planning on doing this on the calculator cam, but those of you that have your calculator handy can figure these out for us and shout out an answer. What is the I think there's 3 or 4 of these. What is the voltage gain, or what voltage gain can be expected from this circuit when R1 is 10 ohms and RF is 470 ohms?
Charlie.
Yeah, you
Charlie.
don't really need a calculator for that. Just 470 divided by 10, which is 47. See, I told you these were easy, and the other ones are very similar to it. There's a few more coming up. What does the gain of an ideal operational amplifier, or how does the gain of an ideal operational amplifier vary with frequency?
Doesn't.
Delta.
That's ideal, yeah, and you got to read the question carefully. The ideal amplifier does not vary with frequency. The real one, of course, diminishes. Okay, here's, we walked through this one, so you might just remember the answer, but what will be the output voltage of this circuit if R1 is 1,000 ohms, RF is 10,000 ohms, and 0.23 volts DC is applied to the input?
Delta.
Yep, that is
Charlie. Oh.
Okay, now
Delta.
notice something here. They give you all kinds of ways to get this wrong. So you need to kind of think through this a little bit. So first thing is the gain. So 10,000 ohms to 1,000, so the gain is going to be 10. You're applying 0.23 volts in, times 10 is going to be 2.3. So now is that negative or positive? Well, because it's an
It's on the
inverted.
inverting.
Exactly. Yeah, that makes it negative 2.3. So if you kind of walk through that thinking, you'll get to it. But you do have to think about it because they give you every possible way to get it wrong here. And
If it was at the positive, would it have been 2.3?
yeah, if it went the other way, then the output wouldn't go the other way. Yep. So if you put in a negative 0.23, then you'd wind up with a positive 2.3. So whatever it is, it inverts. Okay, here's another one that I don't know if you can do this one in your head, but again, they're asking us for the gain. So how would we do that?
68 divided by 1,800.
Well, actually, it's 68 divided by 1.8, because 1,800 ohms is
Yep,
1.8 K. So 68 divided by 1.8, and what does that work out to be?
Charlie.
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 Yep, exactly. Okay, I told you these were easy. You just have to read them carefully. Here's another one. In this case, R1 is 3,300 ohms, and RF is 47 K ohms.
Bravo.
It does work out to Bravo. 47 divided by 3.3 works out to 14. The bigger divided by the smaller. And be careful of K versus ohms. You have to do some unit conversions there. So what is an operational amplifier? Remember all of those big hairy words that we talked about in the beginning?
Alpha.
It is alpha, a high gain, direct coupled differential amplifier with very high input impedance and very low output impedance. Now, if you took this to the extreme, I guess you could say that an operational amplifier, an ideal one, should be able to drive an entire city with a 1.5 volt battery, right? Well, that's not true. What is the function of hysteresis in a comparator?
prevents noise from causing an unstable input or output
would
signal.
be alpha.
Yep,
Alpha.
alpha, correct. Yep. That's the way that they've put it in the pool. What happens when the level of a comparator's input signal crosses the threshold voltage?
Bravo.
Bravo.
It is Bravo. The comparator changes its output state. And we're moving right on to amplifier classes. Yeah, you all are doing really, really good. Now, amplifier classes are something that have been very confusing to students in the past. So I'm going to go through 3 different ways that you can look at this. And one of them will probably resonate with you. And that's the one that will help you answer the questions. So here is first a visual approach. And we've got an input over here. And then we've got outputs shown over here. So with a Class A amplifier, that's defined as an amplifier that's amplifying through the entire waveform. So the input waveform is here, and it's making the waveform bigger on its output, as shown here, all in green. So the green is the amplified portion. Now Class B is a little bit different. With Class B, the transistor or the amplifier is biased in such a way that it's only going to be amplifying 180 degrees of the input waveform. And you might be saying, why in the world would you want to do that? Well, the reason for these other classes is that the Class A amplifier has to be conducting through its entire cycle, meaning it needs to take quite a bit of power. If we only had to conduct on half of the input cycle, we'd only be using half as much power. That's the advantage of a Class B. Now, how would we actually use that in the real world? We're going to come to that. For now, we just need to know that Class B is 180 degrees of the input waveform. Class AB is kind of a combination of the two, this one and this one. We're going more than 180, but less than 360. And again, you're probably wondering, why in the world would you ever want to do that? Okay, we're going to answer that in a bit. And then Class C, a Class C amplifier is just conducting on a portion of the input waveform. So you might be wondering, well, which of these would be most efficient? Well, Class C of the ones that we've looked at would be the most efficient because it's conducting the least amount of time, consuming the least amount of power. Then Class D is shown down here. That's actually even more efficient. They're using something called pulse width modulation. This is a differential kind of circuit here. And then we've got a couple of field effect transistors, a P channel and an N channel. It has an output that is just really, really ugly. But we smooth it out with a filter, restoring it to a nice clean output. Class D amplifiers are very efficient. And these there's places where these are used in real life. We'll talk a little bit more about that. So here's the first pass. All right. So that's one way you can visualize this. We haven't connected it to the applications yet. There is one pool question that asks about Class AB. And that pool question wants you to know that it's going to be greater than 180, but less than 360. So we'll put that out as something to remember. This is the second approach that we can use. There's a bunch of pool questions that relate to this. So here we've got a diagram. Remember I said for a Class A amplifier, we want it to be biased in about the middle of its range. We don't want it to be fully cut off or fully saturated. So a Class A amplifier is biased approximately halfway between saturation and cutoff. So that would be this place right here. So then an AC signal could swing low or high and still be linear, be amplified over that entire range. Now Class B, bias is set right at cutoff, so we're only going to amplify half of the wave. Okay. AB is sort of a hybrid between A and B, operates between the 180 and 360 degree points on the signal cycle, like we saw in the previous slide. And Class C is set well into the cutoff region, so that only the peaks of the incoming signal will be amplified. And then class D, we saw previously, uses switching technology, that pulse wave modulation we talked about, to achieve high efficiency, and it needs a filter to remove the harmonic content. Otherwise, the output is very ugly and very rich in harmonics. So this is the second way of looking at this, and you can see I've drawn lines in here between the class C, or the class A limits are here, class C, class B. Another way of looking at it, this is an expanded version of what we just showed between saturation and cutoff. The various places that the easiest one to see is probably the class A, where we set the bias at this point, it's amplifying plus and minus. C and B, it's less than that. And then the third way that we'll explain it is the way that Kastler explained it, where he was using a flywheel analogy. A flywheel is like a big metal plate. Look at it that way. So in the case of a class A, it's always pushing the flywheel all the way around. Class B pushes the flywheel half of the time, and class C just gives it a little push. All right, now I'll start connecting this to some things we've talked about in the past. Now the RF output circuits that we looked at before, the tank circuits, remember there was a coil and capacitor in parallel, and if we tap that circuit just for a little bit, it starts ringing at the resonant frequency, and it'll keep ringing even when we take the input signal away. So we can kind of see that working its way out here. Let's look at class C, for example. So we're just going to push it a little bit, but that coil and capacitor, the tank circuit, are going to keep on giving each other energy and absorbing energy, and the circuit will continue to oscillate. Oscillate probably isn't the right word, but it's exchanging that energy back and forth at the resonant frequency. I guess oscillate would be the correct word. So that can be a good thing. There's certain modes of operation, like frequency modulation, which is a full carrier mode that's not really sensitive to amplitude at all. Then we've got single sideband, or AM, which are very sensitive to amplitude. So we'd have to have something that was conducting all the way around for single sideband or amplitude modulation. And you can see that the relationship between the input and the output of the amplifier is linear. Whatever comes in on the input is going to be faithfully reproduced on the output. That would be a linear amplifier. That's probably a term you've heard before, used in ham radio amplifiers. So you need something that's linear in order to amplify single sideband or AM. But with FM, or even CW, something like this would be very efficient, because the exchange of energy between the coils and the capacitors and the tank circuit would keep that energy going even when we weren't pushing the flywheel. There's one other concept that I need to share because it's a pool question. This is kind of a strange bird, or it looks like it. We've got two different kinds of transistors. And we've got a circuit with through a transformer. We've got input waveforms being supplied. Now, the way that the transistor is biased, this transistor is only going to be conducting on the negative peak of the input cycle, this one on the positive peak, but they're recombined in the output transformer to produce a waveform that is back to looking like the input waveform. So let's see if these words make sense now. Each active element in a push-pull class AB amplifier. Now let me back up a minute. In this case, we were just conducting on half of the waveform. So this diagram would be showing a class B push-pull amplifier. Well, might there be a problem with that? The problem turns out to be that at these switching points where it goes from not conducting to conducting, we have what's called crossover distortion, where it's kind of hard for the output to be pure if these are switching at exactly those 0 points. So the way that these are actually used in the real world, these amplifiers are biased such that they're running in AB mode, which again is, well, I'll read it. Each active element in a push-pull class AB amplifier conducts more than 180 degrees, but less than 360 degrees. And the reason that they want to do that in class AB is to get rid of that crossover distortion that would happen at these 0 points. And these are the words you need to remember. So this is a review to summarize everything that we've talked about and draw our focus back to the pool questions. So for class A, bias is set about halfway between saturation and cutoff. Class B, bias is set at cutoff. Only 1/2 of the incoming waveform is amplified. Class AB operates between 180 degrees and 360 degree points of the signal cycle, usually just slightly over 180, but this is the way the pool reads. Class C, bias is set well into the cutoff region. And then Class D, 2 pool questions here. Switching amplifiers are more efficient than linear amplifiers because the switching device is at saturation or cutoff most of the time, and it requires a filter to remove the harmonic output. I think I forgot to ask Gary a question here. Did you have a case in all of your experience where you actually were using Class D amplifiers?
Well, as many folks know, I used to work for the Voice of America, and we had overseas transmitting stations with very high power broadcast transmitters. And we were always concerned about budget, and the 2 biggest costs that were involved were personnel costs and power, electrical power. And so we were always looking for the holy grail, the most power efficient transmitters that we could come up with. And Marconi Corporation came out with their model B6128, 500,000 watt shortwave transmitter that used a pair of vacuum tubes, one on top of the other, to generate pulse width modulation. And then it would be modulated by audio coming in, and then filtered and going out as a modulated RF signal. And that was very power efficient compared to conventional high power transformers arrangements, things like that, on earlier transmitters.
I can imagine.
Later on, they converted those vacuum tube pulse width modulators to solid state field effect transistor switching modulators, saving even more power.
Yep.
So.
I wonder what kind of power bills were you guys seeing, or do you even know?
I remember, well, in Kavala, Greece, my last overseas assignment, I was paying a diesel fuel oil bill, because we generated our own power, of $200,000 a month.
Wow. Okay. Well, most of our ham applications won't get that expensive.
Yeah, exactly.
All right. So again, I wanted to show this slide just so you could kind of get everything in the context to the pool questions. One other topic before we look at some questions. So I mentioned for CW or FM, a nonlinear amp will work. That would be something in the B or C category. For AM and SSB, a linear amp is required, Class A. This isn't 100% of the case, but I'm simplifying it for you for the purpose of our studies. So using a Class C amp for amplifying a single sideband phone signal will result in distortion and excessive bandwidth. And how does one measure that, you might be wondering? Well, there's something called the two-tone test, which I'll just mention in passing because Gary's going to be covering it in a couple of weeks in more detail. But if you take two tones and apply it to the signal or to your amplifier, you might be getting a pattern like this. And this one looks like it's about 10, 20, 30 dB below the input. This one here is much worse. So you can see we've got all kinds of splatter and distortion going on. So I'll just mention that the two-tone test is the way that this is categorized, and Gary will get into that in more detail in a future class. But it's important to know the blue text here. Okay, so what? We'll see if any, how much of this got absorbed now, since I presented it 3 different ways. Hopefully, all of it. For what portion of the signal cycle does each active element in a push-pull Class AB amplifier conduct?
Alpha.
It is alpha, more than 180 degrees, but less than 360. What is a Class D amplifier?
Alpha.
You're correct. An amplifier that uses switching technology to achieve high efficiency, saving some of that diesel expense that Gary was paying. What circuit is required at the output of an RF switching amplifier?
Alpha.
It is alpha, a filter to remove harmonic content because the output looks terrible otherwise. What is the operating point of a Class A common emitter amplifier?
Alpha again, a lot of alphas.
Yeah, that's right. Don't expect that on your exam though, because they'll be all rearranged, right? But it's approximately halfway between saturation and cutoff. Which of the following is the likely result of using a Class C amplifier to amplify a single sideband phone signal?
Delta.
Delta.
Yep, signal distortion and excessive bandwidth. Why are switching amplifiers more efficient than linear amplifiers?
Delta. No.
No.
No. Bravo.
Bravo, yeah. I don't know that I've expanded on this at all, but it is Bravo. The switching device is at saturation or cutoff most of the time, so it requires a lot less power. So it's only on a very small part of the time. And this would be a perfect time to take a break, and we're right on, we're tracking right on the time I was hoping that we would be. Well, we're going to come back to section 6.2. Oscillator circuits and crystals and signal processing. So we'll go ahead and we'll take our 5-minute break at this point, and we'll be back at you with some more good stuff. Okay, we're back. I hope you did something fun during your break. Got your mind off this for a few minutes. We're going to be looking at signal processing and oscillator circuits coming up next. All right, so the concept of an oscillator circuit is pretty simple. You have an amplifier, and if it has gain that's more than 1, in other words, an amplifier that's got more coming out of it than going into it, that would be a gain of more than 1. And you've got some kind of a filter between the output and the input, the amplifier will turn into an oscillator, meaning that it will continue to produce a signal at the frequency of the feedback circuit. So if we've got positive loop gain, meaning greater than 1, and the feedback is in phase, the circuit will oscillate. It'll be making sine waves. There's lots of places where we want that. So if you think of a public address system in an auditorium, you've all heard that wonderful screeching howl sound. What we've got there going on is a microphone and an amplifier, and there's actually resonance in the room acoustics, and that's what is providing that network that will tune the feedback. So normally when you hear an amplifier screeching in an auditorium, it's happening at a particular frequency. It's the room acoustics that actually form that filter. Interesting. Then, so those are good oscillations, okay? That's what we want to use in radio. They're under our control, and we're going to be creating them. And then we've got instability and parasitic oscillations. And some people call children parasitic oscillations. So look at all this mess that's going on over here. So parasitics are oscillations that are not related to the operating frequency of an amplifier. They may be above or below the operating frequency. So the amplifier is taken off and become an oscillator, and you didn't mean for it to do that. That's a bad thing. So it's not the same. We saw intermodulation products in a previous picture where there were specific frequencies that were coming into a circuit, and the output of that circuit was a combination of those frequencies coming into it. That's not the case here. Parasitic oscillation, it'll just take off on a frequency that you may not even be expecting. And I think you had a story here too, didn't you, Gary, Voice of America, where you're blowing up capacitors or something?
Oh, well, yeah, we had in Liberia a General Electric 250,000 watt shortwave transmitter, and we kept losing vacuum capacitors. So they were used for coupling and for tuning. You know, about $1,500 back then in 1989. Ultimately, we couldn't figure out, everything tested fine. It was intermittent, of course, and it turned out to be an output tube that would oscillate at VHF. And our measurement equipment couldn't detect that because we weren't looking for it. But ultimately, if we pulled the tube out, put a new tube in, neutralized it, set it up, then we didn't lose vacuum capacitors anymore. Parasitic oscillations, not wanted.
You'd never expect an HF transmitter to be generating a VHF signal. That's what was going on. So excessive gain or positive feedback may cause amplifier instability. And unwanted oscillations can be prevented by installing parasitic suppressors and or neutralizing the stage. Now, neutralization, we'll have a picture of that coming up. Parasitic suppressors, sometimes it can be predicted in the design of a transmitter that it will be susceptible to oscillating at an unwanted frequency, and they can install parasitic suppressors to prevent that particular frequency from taking off. And how do we neutralize something, you might be wondering? An RF power amplifier can be neutralized by feeding a 180-degree out-of-phase portion of the output back to the input. Would damp out that positive feedback that's trying to make it oscillate. So here's a diagram. Now here's a triode amplifier. We've got some amount of capacitance between the grid and the plate. Well, that would be feedback that would be positive. So that would potentially encourage the circuit to oscillate. And then there's a capacitor up here, C sub n, a neutralizing capacitor, that picks a point in the output of the circuit that's 180 degrees out of phase with the input and feeds some of that signal back, which neutralizes the amplifier. Now, if you have a tube amplifier or ever buy one, they're available at pretty good prices on the ham market. Normally, in the documentation for the amplifier, there will be a neutralization procedure that you can use if you ever change the tube. Because the tubes are slightly different, even though they might have the same part number, the internal capacitance varies somewhat between one tube and another.
And that's another benefit of a grounded grid linear amplifier. Neutralization is not required.
Okay, that's a good thing to know. So that's the concept. If you can neutralize the amplifier, follow the directions in your manual, that will prevent that problem from happening. Oh, and I did get a picture of Gary's transmitter here.
That was the one, well, not that transmitter, but that model transmitter that was causing the loss of the vacuum capacitors.
Now, we were talking about the single sideband contest coming up in a couple of weeks, and I think Gary's busy installing one of these in his garage right now.
No.
Not really. Wouldn't that be nice, though, for breaking pileups?
I can't afford the power bill.
Yeah, that's right. So we're going to talk about desirable oscillators now, not the ones that are causing us problems. There's three different flavors, Colpitts, Hartley, and Pierce, that are important to our studies. Colpitts depends on a positive feedback via a capacitance divider. So here's the Colpitts circuit, and here we can see the capacitive divider. So how in the world, see, there's a couple of pool questions involved here. How in the world are you going to remember that? Well, if you can associate Colpitts starting with a C, and it works via a capacitive divider, capacitors, Colpitts, that'll help you associate that one. Hartley, there isn't, although they do ask what the three types are, there aren't any details about how it gets its feedback. If you're wondering, it gets it from a tapped coil. Pierce, okay, this is basically like the Colpitts circuit, but it uses a quartz crystal. We're going to be talking more about crystals coming up. So it's the most stable of the three. A quartz crystal is a piezoelectric device. So P for piezo, P for Pierce, that works. It might help you get it. And here's another one. This one's kind of goofy, but a broken piece of quartz can pierce your skin. Quartz crystal, pierce. And I'll actually have I can show you what a broken crystal looks like coming up in a second. Now the crystal oscillators that sometimes in QRP radios in particular are sometimes referred to as a rock-bound transmitter. In other words, it's tied to that particular crystal. Another term that sometimes you can hear is the term rock bender. It is possible with capacitance across the crystal to shift it up and down in frequency a little bit. So that would be an example of a rock bender transceiver. Just some terms you might run into in your ham radio career, especially if you do QRP. Microphonics, now this is kind of interesting. If you tap a microphone, you normally hear it in the speaker, right? Well, if you tap an oscillator circuit, sometimes you can hear it act like a microphone. If that happens, that's called a microphonic. So it's caused by changes in oscillator frequency caused by mechanical vibration. So the slight changes in capacitance that occur when you flex the metal around the oscillator or bang on an oscillator tube, sometimes you can get these microphonic responses, which are undesirable. So the most common in home retransmitters, anything that you buy commercially, of course, they will have worked through all of this for you. So the solution is to mechanically isolate the oscillator circuit from its enclosure. Some of the earlier ham transmitters had the oscillator circuits shock mounted with rubber feet inside the transmitter housing. So that was one way that they could mechanically isolate the circuitry from the larger enclosure. It is possible for components to become microphonic as well. I've seen transistors and other parts, if you tap them, you'd be able to hear it in a speaker. It's not supposed to happen. You got a bad part if that's the case. And then we'll talk about crystals a little bit. Here's some crystals, and if you were a ham back in the novice days, when it was legal to only use a crystal to control your transmitter frequency, here's some 40-meter crystals shown, some other things. This is the inside of one. A crystal is a piezoelectric device, very high Q, generally over 100, very sharp but very stable, very precise. And an interesting bit of history, back in the day, hams would actually grind their own crystals. They'd start with a crystal on a frequency that they didn't want and try to change it. They actually had grinding compound. You could take the crystal apart and whale away on, in southern term, on the quartz crystal face. Some people would use toothpaste, believe it or not, and rub that to lower the frequency, or they'd use pencil lead to raise the frequency, actually changing the physical size of the quartz. So a little bit of ham history for you there. I'd like to show you, I brought some along as samples over on the calculator cam. So these are just some that I happen to have in my collection that I brought along for demo purposes. This is a crystal that may be used for, you see these quite often in microprocessor circuits to operate provide the clock signal for the microprocessor. These are a couple different sizes of crystals. These are ham crystals that are two in the 40-meter band, one in the 80-meter band. All CW. And this is a picture of the FT240 style 42 crystal that I took apart, so you could kind of see the innards. Here's a spring that holds everything together, cover plate. Got two pieces of metal that sandwich the quartz layer in between. And you can see the contacts here. I don't have the quartz piece itself. I don't know where I lost that, but you can get an idea of what we're dealing with there. And these, I'll turn it over. It kind of looks like you'd expect it to. Now this one here is one that I took apart, and I'll zoom in on that a little bit. So here you can see that we've got the crystal base and the two connectors, pins, and connected up to the crystal, but the crystal itself has been broken. I don't know if I broke it when I was taking it apart or just what happened. So when I said that a piece of quartz can pierce your skin, well, maybe that's a picture that will help you associate crystal and pierce oscillators. So just kind of wanted to give you a little picture of what was involved there. Some things out of my demo box. I collect some of these things at ham fests, and just for the purpose of sharing them with our classes. In fact, a lot of times when I tell somebody that's selling some of this kind of stuff at a ham fest that we're using it for ham radio classes, they'll just give it to me. So I'll have an example of some of that in just a minute. So piezoelectricity. All right, what is that? It's a characteristic of materials that generate a voltage when stressed. I've got a picture of some kind of piezoelectric material here. I don't know that it would be a quartz crystal. You wouldn't want to bang on that with a hammer. Kind of a cartoon, I guess, in a way. But it's showing if you bang on it, you'll generate a voltage. So piezoelectricity, characteristic materials that generate a voltage when stressed, and they work the other way too. They flex when a voltage is applied. That's why our crystal oscillators work. Okay, it is a mechanical deformation of material due to the application of a voltage. So the pool approaches it two different ways. There's an article here if you want to get into it in a little bit more detail. Now there's a problem with any kind of oscillators, and that's thermal drift. So when the equipment starts to warm up, that'll change the frequency, the operating frequency. Crystals are less susceptible to that, but it is a problem there too. So you can minimize the thermal drift by using parts with a low temperature coefficient. And one in particular that's cited is what's called a negative positive zero capacitor. That means as the temperature increases or decreases, the capacitance won't change. Most parts will have some kind of a temperature coefficient, but these parts can be used to minimize that. And then we've got something called crystal ovens. And I did find a couple of these at a ham fest that I want to show you. We'll walk over to our other demo table. So hopefully you can see these. We've got two different flavors. And notice it's got an octal base. Make sure this is showing up. Yep. And I loosened the screws so we could open it up and see what's inside. And look at that, there's a crystal in there. So how do these things work? You might be wondering. Well, there's a heating element here. And when you turn on the radio, this will increase in temperature to something that's well above ambient, might be 150 degrees Fahrenheit or maybe more. And then when it gets to that set point, it'll open up and it'll regulate the temperature within a fairly narrow temperature range, isolating the crystal from the ambient temperature around it. So that this is one flavor. We've got another one here that's a little bit different. Same idea, octal base. It's an older piece of equipment. You don't see this very often anymore. This one's a little bit different. This has got a brass outside and a copper cover on it. I'll pull that off. And you can see that we've got some insulating material here. Take that off. And inside this one, we've got a pair of crystals. They're listed as 1,000 kilohertz. And they're both 1,000 kilohertz, so this is probably some kind of a filter. But the principle is the same. These are crystal ovens that heat up and then maintain the temperature so that the crystal frequency remains stable. Even though crystal frequency is fairly stable to start with, this gives you even a better temperature range. Used in older equipment. I think these came out of a 2 meter, not 2 meter, but 100, what they called the VHF transceivers. I know Motorola used them. I used to work at a Motorola service shop, and we still had some of this stuff we had to maintain. So I'll wander back to the other position. And we just talked about what are called crystal ovens. A little bit more on quartz crystals. Now, if you can kind of picture this diagram, it'll help the words make sense. The equivalent circuit of a crystal is series RLC. So here, resistance, inductance, capacitance. In parallel with a shunt C, shunt capacitance, representing electrode and stray capacitance. So inside this little can here, if you were to analyze what's going into it, coming out of it, it would wind up acting like this circuit right here. So the equivalent circuit, series RLC in parallel with a shunt C, and the shunt capacitance is the electrode and stray capacitance within this package. So this is a circuit symbol. Not to be confused with the capacitor that is needed to be used outside a crystal. So to ensure a crystal oscillator operates on the frequency specified by the crystal manufacturer, provide the crystal with a specified parallel capacitance. So when the crystal manufacturer will say, take our crystal and put that in parallel with a certain value of capacitance to make sure that it acts the way that it's supposed to, not to be confused with this one here. So two things to remember. Now, back in the good old days, back in the novice days, the mid-60s, before and after, Gary and I were both licensed back at that time, when you were able to pass your general exam, you were allowed to use what was called a variable frequency oscillator. Here's an example of a night kit, I believe. And instead of having one or two crystals that you could plug into your transmit and operate on those frequencies only, you could now operate over the entire band. Boy, you really were in business when you were able to do that. Of course, we think that's almost silly today, because any modern transceiver, you've got the big knob on the front, you can go to any frequency that you want. This was a big deal back then. So it used to allow an oscillator to tune a full range, in this case multiple ham bands. They usually used the Colpitts or Hartley circuits, and of course they could drift with temperature, and sometimes microphonics were a problem. So either the capacitance or inductance would have to be variable, depending upon if it was a Colpitts or Hartley circuit. Capacitors were most common, and of course they weren't as stable as crystal oscillators, but when they first came out, hams really loved these things. So microwave oscillators, most of us aren't going to be dabbling in microwave, but there are microwave frequencies, ham bands, that are specialist sorts of things that you might get into further on in your ham radio career. So microwave oscillators, they can come from three common sources. Something called a GPS disciplined oscillator, where you've got an oscillator that corrects itself according to GPS signals received from satellites. Rubidium stabilized reference oscillator, or temperature controlled high Q dielectric resonator. You can Google these if you really want to know more, but we're going to have an all of these answer coming up. So when you see that, just be aware that these are all used to generate signals at microwave frequencies, microwave oscillators. All right, and then right on to some questions. What can be done to prevent unwanted oscillations in an RF power amplifier? Charlie, installed parasitic suppressors and/or neutralize the stage. What are three common oscillator circuits? This is where they wanted you to know the three names. Delta, Colpitts, Hartley, and Pierce. How is positive feedback supplied in a Colpitts oscillator? Charlie through capacitive divider. C for capacitance, C for Colpitts. How is positive feedback supplied in a Pierce oscillator? Delta. Right. Piezoelectric, Pierce, or broken crystal pierces your finger. And which of the following is a technique for providing highly accurate and stable oscillators needed for microwave transmission and reception? Delta. Yep, all of those things. What is piezoelectricity? A lot of words to read there, but hopefully.
Charlie?
Yep, it is Charlie. A characteristic of materials that generates a voltage when stressed and that flex when a voltage is applied. That's exactly how a crystal works. What is the equivalent circuit of a quartz crystal?
Bravo.
Okay. Well, it is alpha. Series RLC in parallel with a shunt capacitance representing electrode and stray capacitance. And there's a little shortcut to this one. It's the only answer that has the words shunt capacitor in the answer. Shunt C, it's called here. Which of the following is an aspect of the piezoelectric effect? Alpha, yep. Mechanical deformation of material due to the application of a voltage, which is how our radio crystals vibrate. And of course, the effect works two ways. They've only asked for one of them here. Which of the following ensures that a crystal oscillator operates on the frequency specified by the crystal manufacturer?
Oh, no, bravo.
Good, you fixed it. Provide the crystal with a specified parallel capacitance. What is a microphonic?
Charlie.
Charlie.
It is Charlie. Changes in oscillator frequency caused by mechanical vibration. How can an oscillator's microphonic response be reduced? Be careful on this one. Something that's very tempting.
Alpha.
Okay, microphonic response.
Calling the microphonic.
Delta.
Delta, yes, mechanically
Delta.
isolate. Yep. Now, the temperature drift, that's where alpha would come in. But they're asking microphonics, that's mechanical. Oh, here's the one that you wanted. Which of the following components can be used to reduce thermal drift in crystal
So that
oscillators?
would be alpha.
That would be
Yeah.
alpha. Yeah, we sure
That's
love
the
our
alpha one.
we sure love our alphas. All right, we're doing super here. A couple more topics to cover. Frequency synthesis. This sounds like some really complicated stuff. There's only 2 pool questions, and I've got some things to look for to make these easier. First of all, phase lock loop. Now the earliest, when frequency synthesis became popular in ham transceivers, phase lock loops were kind of the first phase of that. They were there before DDS, which we'll talk about next, direct digital synthesis. But phase lock loop, now here's some big words for you. An electronic servo loop consisting of a phase detector, low-pass filter, voltage-controlled oscillator, and a stable reference oscillator. Well, let's look at the picture and just get an overview of how this works. So we've got an oscillator that's kind of running free, I guess you could say, and we've got a divide by N counter going on here, and then we've got a crystal reference. This is a picture of a crystal. So what happens is that there's the output from the oscillator that is otherwise free running would be compared to the reference frequency of something that was crystal based, very stable, and that would go into a phase comparator. The output of that phase comparator would go through a filter and then back to the voltage controlled oscillator. So what's happening here is we're going to lock this oscillator onto a reference signal that is crystal based. So what's going to be happening is it allows a radio's VFO, variable frequency oscillator, to have the stability of a crystal oscillator. And this voltage controlled oscillator can only work over a certain range. So the capture range is the frequency range over which the circuit can lock. So that's all built in by the designer of the equipment. So the one characteristic of a phase lock loop is it's always kind of hunting, that this is trying to wander high in frequency or low in frequency, and it gets compared then to the reference, the crystal oscillator reference, and then gets adjusted by the phase comparator to keep it locked right on frequency. So it's drifting around a little bit, or hunting as they call it, for that exact lock. That'll be important in one coming up. That hunting causes something called phase noise as the frequency is changing slightly. And then phase lock loops, a little bit more on phase lock loops. Okay. Any short-term variations in the frequency output will cause phase noise, meaning that the frequency will shift up or down a little bit, the phase is changing. Phase noise is the major spectral impurity component of a phase lock loop synthesizer. And interestingly, and this will make sense when we talk about it, A couple of functions, well, certainly we want to generate a frequency. So frequency synthesis and FM demodulation. Well, why would we say FM demodulation? Well, a signal being compared to this output, if it was a frequency modulated signal, the difference between this output and the FM signal that we were listening to would be an audio frequency, because audio is what is causing the frequency to shift in a FM circuit. So that's why both of these functions are there. First one is real obvious. The other one, FM demodulation, might not be so obvious, but that's why it works, because the frequency is changing. Now we'll move on to the DDS, direct digital synthesizer. More big words here. Uses a phase accumulator, a lookup table. Notice I've bolded a couple things here. Lookup table, digital to analog converter, and a low-pass anti-alias filter. So it uses a lookup table containing amplitude values that represent the desired waveform. So it's putting out a bunch of pulses, and then it has to use a lookup table to say, well, how big should the signal be for each one of those pulses? And that actually traces out a sine wave. So it uses a lookup table containing amplitude values that represent the desired waveform, which would be a sine wave. And then we've got all of this jagged stuff going on here, which would be bad. It would be loaded with harmonics, noise. So spectral impurities, or low-pass filter, smooths out the output to a pure sine wave. Here's a jagged sine wave, and then a filter makes it smooth. So spectral impurities are spurious signals at discrete frequencies. You can see that we got all kinds of funny things going on here. So in a radio that's using direct digital synthesis, sometimes with the antenna disconnected, you will, on some of the ham bands, occasionally be able to see a signal that's sitting there all by itself that happens to be a spurious signal that's coming out of the direct digital synthesizer. And I've seen radio manuals that say that on these specific frequencies, you may hear a birdie, as they call it. And that's what those are. So the trick here to distinguish between phase lock loop, okay, a phase lock loop is going to have a voltage controlled oscillator. That's the word to look for. A direct digital synthesizer is going to have a lookup table to create that sine wave, and a low-pass anti-alias filter. The reason that I picked those is because that's what you need to look at in the pool questions. Oh, look at that. What type of frequency synthesizer circuit uses a phase accumulator, a lookup table, digital to analog converter, and a low-pass anti-alias filter?
Alpha.
It is alpha. That's the direct digital synthesizer. And some of the magic words are here that will help you to get there. You might need to look at this a couple times and be sure you associate those. What information is contained in the lookup table of a direct digital synthesizer?
Alpha.
It's not.
Bravo.
It's Bravo.
I'm sorry, Bravo.
Yeah. All right. It's okay to erase your answer on your test sheet as long as it's clear to the VE team that what you meant it to be. Yeah.
I was looking right at Bravo.
Okay, that's all right. It's all right. What are the major spectral impurity components of direct digital synthesizers?
Charlie.
Yeah,
That is Charlie. Spurious signals at discrete frequencies. Remember that? Or birdies. Yep.
Tweets.
What? Yeah, tweets, X's. What is a phase lock loop? Okay, big words. Let's see if we can remember the key words here.
Charlie.
Charlie.
It is Charlie. You might see servo loop here and say, oh, that's what it is, but there's two answers with servo loop in them. So the phase detector and voltage controlled oscillator are the words to be looking for. Which of these functions can be performed by a phase lock loop?
Bravo.
Bravo.
Frequency.
Bravo.
Yep, frequency synthesis and FM demodulation. Take a quick look at mixers and modulators. We've touched on this in other chapters, other sections already. These are more building blocks for radio. So mixers are used to change the frequency of a signal. And I know we were talking about mixer math, where you've got an input frequency and a local oscillator frequency. Then you've got the sum and difference frequencies coming out of them. So it converts incoming frequencies to an intermediate frequency. And these are also used in transmitters to shift frequencies around. We'll see more of that next week. So spurious mixer products are generated when input signal levels are too high. We got a picture of a mixer up here, and that's probably a pretty good analogy, because yeah, the electronic mixer mixes things up. You don't want too much of a mess. You don't want the stuff splashing out of the bowl, as would happen if the levels are too high. So the mixer output, two input frequencies, and the sum and difference frequencies. And then we're going to want to filter one, because that's the one that we will want to use, the intermediate frequencies. It's done with a filter. Modulation, we've seen this picture before. We've got a carrier signal. Now, you would think that if you were in the same room with somebody, you could just speak and they would hear you. Okay, that would work. Maybe if they were in the house next door to you, if you yelled really loud, they might hear you. But if they were on the other side of the country, that'd be impossible. So we need a carrier signal. We need some kind of a signal that will carry that audio information across the country on an RF signal. So that's why it's called a carrier signal. So the process of modulation, we're going to take the audio signal and impress it on the carrier signal to wind up with something that looks like this. And you can almost visualize, in order to recover the audio from that RF signal, all we would have to do is rectify it. Then we would get something that looks like this, the outline of the audio signal. And then if we filter it, it would come back to being, in this case, a sine wave. So modulation is the process of adding information to the RF carrier. So you can send it off into space. And then there's kind of an oddball concept here that comes up more in microwave systems than it does in single sideband and CW. But baseband is the frequency range occupied by a message signal prior to modulation. So that would be the audio. In the case of single sideband, that would usually be the frequencies of 30 to 3,000 or up to 3 kilohertz, the audio band. That's what you're applying to the carrier signal to send it off into space. So just a definition there for you. Frequency range occupied by a message signal prior to modulation. It gets a lot more complicated than that in some other cases that we don't need to get into right now. It can be voice or data. So we saw before that amplitude modulation is a carrier in 2 sidebands. And the amplitude of the RF signal down here depends on the amplitude of the audio signal. And here's a picture I think we've seen before. We've got audio frequencies, we've got a carrier signal, and for AM we've got a lower sideband and an upper sideband. And single sideband is a form of AM signal. We just get rid of the carrier in one of the sidebands. So we've got 2 ways to do this. We've got the filter method. Now that uses what's called a balanced modulator. A balanced modulator suppresses the carrier, so we can get rid of the carrier. And then we follow that by a filter to filter out the sideband that we don't want. So a balanced modulator removes the carrier, bandpass filter removes one of the sidebands, and then you can put a lot more RF energy into the one remaining sideband, so you can talk further. So we've got the filter method and then the quadrature method or phasing method. These are the 2 ways of generating single sideband. This uses a 90-degree phase shift to cancel the carrier and one sideband, a bunch of mathematical magic we'll talk a little bit more about next week. It's really hard to do with analog circuits, although it has been done. It's very easy to do with digital signal processing. There's a mathematical method called the Hilbert transform that does that. So quadrature method is usually employed in radios using DSP. Pretty much all modern transceivers are going to be doing it this way. So I found a link we don't have time to look at this evening, but the phasing method, there's some technical information on how this works if you're curious about that. And there's one here that I'm going to highly, highly recommend you look at between now and next week. It's called Signal Wars, single sideband. When single sideband first came out, there were heated debates in the ham community saying, well, single sideband is going to ruin ham radio. Gary's got a comment.
It's not ham radio. It sounds like Donald Duck.
Donald Duck, yep, it's slop.
The same argument used now for FT8.
Yep, and this 9-minute video talks about all of that, how it developed, the wars that were going on in ham radio, including things like FT8. Very entertaining. You definitely want to watch that video. Questions. What are the principal frequencies that appear at the output of a mixer?
Charlie.
It is Charlie. Some real nonsensical answers there on the distractor options. The two input frequencies along with their sum and difference frequencies. What occurs when the input signal levels to a mixer are too high?
Alpha.
Alpha, spurious mixer products are generated. What is meant by the term baseband in radio communication?
Bravo.
That is Bravo. Yep, and the easiest way to think of that is the voice frequencies in a single sideband transmission. A baseband can get much more complicated than that, but we don't need to get more complicated than that for this chapter. What is one way to produce a single sideband phone signal?
Alpha.
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 We sure are enjoying our alphas tonight. Use a balanced
Yep.
modulator followed by a filter. Yep. And then we'll touch on frequency and phase modulation in chapter 8, I believe. We're going to have a lot more on frequency and phase modulation and other ways of modulating carriers, but just some basics for tonight for this chapter. So frequency modulation, here we've got a carrier and audio like we saw for the AM case, but notice what's happening here. In this case, it's the peak of the audio where it's, okay, here's the carrier, but we're going to be stretching that out. We're actually going to be lowering the frequency at this part of the audio frequency. At this part of the audio frequency, we're going to be increasing the RF frequency. So you can see this bunching up and stretching out. That's the concept of frequency modulation. We're varying the frequency over a range. It might be plus or minus 5 kilohertz for applied signals coming in to the modulator. How do we do that? Well, we use a reactance modulator. You might remember from Gary's discussion of P and N junctions. If you reverse bias a junction, this depletion region becomes wider. So, like the plates of a capacitor, they become further apart, which reduces the capacitance. And these are the diagrams, or the circuit symbols for varactor modulators. So, a reactance modulator produces FM or PM signals by varying a capacitance. We've got something called direct FM. That's where we're actually directly changing the frequency of an oscillator. FM phone signals can be generated via reactance modulation of a local oscillator. So we're actually connecting directly to that oscillator and changing its frequency. Or with indirect FM, also known as phase modulation, uses a reactance modulator to vary the reactance in a tuned RF amplifier that occurs after the oscillator. They're actually changing the phase, which from the point of view of a received signal, seems like it's changing the frequency. So it shifts the phase of the signal, which on the received side is very similar to varying the frequency. The phase is changing, but the human ear can't really hear that. So FM and PM sound the same on the receiving side, and then I added these words, sort of. We'll explain that. So here's a couple of diagrams from Kessler. He's got two flavors. He's got frequency modulation and phase modulation. Now, as I said, hopefully this will link it for you. Frequency modulation, we've got the audio directly changing the frequency of the oscillator itself, generating a frequency modulated signal, goes through an amplifier and out the antenna to your local repeater and talk to your friends. Phase modulation, now notice what's happening here. Here the audio is going into a device that's called variable frequency delay, also a varactor diode, but it's after the oscillator. So we're changing the phase of the signal at that point, which sounds or acts just like direct FM on the receive side, goes out through an amplifier and out the antenna. The most common way of generating FM communication, if you want to call it that, is via this method, phase modulation today. So with direct FM, modulating the oscillator directly, with phase modulation, or indirect FM, we're modulating a stage behind the oscillator, or further down the signal chain. As shown here, audio changes the oscillator frequency. With phase modulation, indirect FM modulates a stage after the oscillator. Now, here's something that's going to lead into our next topic. Phase modulation distorts the modulated audio in a very specific way. Just hold on to that thought for a second. We're going to get into the concepts of preemphasis and de-emphasis. A phase modulated or indirect FM signal boosts the higher audio frequencies. So what happens is a 300 hertz audio signal, audio tone, versus a 600 hertz. The 600 hertz is going to be twice as loud as it's being transmitted. So we've got this preemphasis effect going on. We're going to be emphasizing the high frequencies, and it's going to sound terrible on the receive side. So how do we fix that? Well, here's our preemphasis going on here. We use a de-emphasis filter on the receive side. That flattens it back out again. So here's the preemphasis, the de-emphasis. We wind up with flat audio. There's a article here that there's a link if you care to learn more about that. So this is free with phase modulation. It's it's the physics of phase modulation. It's going to have this preemphasis effect. All right, that doesn't happen with direct FM, because direct FM does not preemphasize the high frequencies. The trick that is used is that a preemphasis network is added to the speech to boost the higher audio frequencies. So we get that for free in phase modulation. We have to add it for direct FM. Then they both look the same on the receive side. So we can use a de-emphasis network. So if we're doing direct FM or indirect FM, they're going to sound the same. So in the context of the pool questions, it says de-emphasis is commonly used on FM receivers for compatibility with transmitters using phase modulation. It actually helps for both because of the way we discussed how this works. But this is what you need to know for the pool. Also reduces high frequency noise. So here's a couple of circuits, just to reiterate what we just talked about. Preemphasis, there's a preemphasis circuit. You can see it's a combination of capacitance and resistance that causes this curve causes the upper frequencies to be emphasized. De-emphasis is a different kind of filter that makes it go the other way and flatten it out. So preemphasis is not needed for phase modulation because you get it for free. It's implemented for direct FM so that over on the receive side, they're both being received the same way. So it reverses the preemphasis and audio is returned to normal. There's an article on that if you want to know more. We'll very briefly touch on detectors and demodulation. Okay, we use this to recover information from a modulated signal. An RF carrier, there's information there, but you can't really detect what it is. That's the idea of the metal detector. So for AM, we talked about, it was kind of obvious from the way it's generated that a diode envelope detector, it works by rectifying and filtering the RF signals. So this is what's coming in. You rectify it and filter it, and now you've detected the AM signal. Product detector, associate that with demodulating single sideband signals. Also works for some of the digital modes in CW. Now remember, with single sideband, we suppressed the carrier. We need to add that back in order to detect the audio. So that uses what's called a beat frequency oscillator to achieve that. FM uses a frequency discriminator. It's a circuit for detecting FM signals. So you just need to associate these modulation types and what we need to decode them. Next week, we're going to be talking about direct conversion of signals, software-defined radios. More on that next week. So single sideband, we already saw that we've got these two methods of doing it, the filter method and the phasing method. For SSB demodulation, product detector. Generating FM, just reviewing these to bring it all together. Change capacitance with a reactance modulator on oscillator. That's direct FM. In direct FM, we're changing the capacitance with a reactance modulator at a stage after the oscillator. We already talked about that. And we use a frequency discriminator to detect FM. The final few questions. Which of the following can be used to generate FM phone signals? FM.
Bravo.
Bravo, reactance modulation of a local oscillator. What is the function of a reactance modulator?
Delta.
Delta, produce PM or FM, phase modulated or frequency modulated signals by varying a capacitance, yes. What is added to an FM speech channel to boost the higher audio frequencies?
Delta.
Delta, that's
Delta.
the pre-emphasis, yes. Why is de-emphasis used in FM communications receivers?
Alpha.
It is alpha for compatibility with transmitters using phase modulation. What is a frequency discriminator?
Delta.
Delta.
Delta, a circuit for detecting FM signals. Then how does a diode envelope detector function?
Alpha.
Alpha, again, by rectifying and filtering of RF signals. And then what type of detector is used for demodulating single sideband signals?
Charlie.
Charlie.
That's the product
Charlie?
detector. Yes, yeah, we went through that pretty fast. It's just a matter of associating the modulation types and how you detect them. And that wraps us up for tonight. I think my pay is going to be docked because I went 30 seconds over our time limit here. But the second part of Chapter 6 is for next week. So finish reading the chapter, and I'll be sending out an email, and we'll wrap it up. This is a lot of stuff in this chapter, mostly fact-based. Any comments, Gary?
No, my mic on? Thank you. There we, no, I think you did a great job there, and I think we've probably burned them all out.
Yeah, that's a lot of stuff. So review it in the coming week, and watch for an email, and we'll nail the second half of the chapter next week. Thank you all for your kind attention and for hanging in there with us tonight. A lot of
Good on
stuff.
ya.
Thank you, guys.
Yep, you bet.
Oh, wait.
Thanks, 73.
You bet.
Dave,
Yes.
I'm still awake.
Oh, thank you.